Welcome to 60 Minutes On, From Theory to Project Practice. This webinar is organized by the Clean Energy Transition Partnership. The webinar series will hopefully help project proposers and project managers to implement their solutions according to the most advanced and international recognized practices for a maximum impact of their projects. Welcome to the 60 Minutes on Cybersecurity webinar organized by the Clean Energy Transition Partnership, Transition Initiative number 1 on integrated energy systems. These webinars want to foster a common approach to ensure your project a maximum impact in terms of capability to scale up and also to replicate your project results. We all know that digitalization is a very strong enabler for all aspects of the integrated energy systems. It allows observability, controllability, stability, efficiency, and so on. However, digitalization has advantages and risks. Among risks, cybersecurity is a very important risk, and it is the subject of today's workshop. As usual, we are going to have 2 sessions. In the first session, a worldwide renowned expert will speak about the main concepts behind our cybersecurity threat. This is going to be the theory. Practical application of the concept of cybersecurity by design will be then explained on the basis of real cases. And this time, in this example, we will go to Italy. So let us start. Our expert of the theory is Stefan Fries. He comes from Germany, he comes from Siemens, and he is going to be our guide through the basic concepts, the standard, and the system design. So, Stefan, the floor is yours.
Hello, my name is Stefan Fries. I'm with Siemens Technology, working in the field of cybersecurity, technology, and trust. And I would like to provide an overview about the cybersecurity in power systems and specifically give an overview about connected regulation and also standardization. First of all, to give you a little bit of my background, as said, my name is Stefan Fries. I'm working as a principal engineer in the area of security technologies for more than 25 years meanwhile. My main focus lies in security architectures and applying cryptographic algorithms and cryptographic techniques to protect specifically critical infrastructure like the power grid. And with that in mind, I'm engaged in standardization in different standardization organizations like IEC. That is one I will describe afterwards in the presentation, and also IEEE and IETF. So let's dive into what does digital grid, or what does a critical infrastructure digital grid mean. What you see on this picture is the classical chain of power generation. So starting from the left side, we see the centralized generation, which then feeds in the energy to the transmission, and that is the high voltage area. Then it goes further down to the medium voltage area in the via the transmission network to the distribution network, which copes with medium voltages, and then it goes further down to the prosumers. That is the low voltage area. It's around 400 volt. So that would be the classical way of energy. Meanwhile, we also have decentralized energy resources, which means that there are renewable energy resources that can provide feed into the generation in the central facilities, but also in the distribution network, and obviously also on the prosumer side. So we all know that house owners or also industrial plants have solar farms or even have wind farms where they can produce energy and also consume locally the energy. What you see also in this picture here is that we have on the boundary of certain networks, like the transmission network and the distribution network, we have different substations. Such a substation is there to basically do the conversion of energy and take care that there is no shortcuts in energy and things like that. So besides that, so this is a physical infrastructure, and besides that, we also have an information infrastructure that takes care that the digital grid is reliably working. And this information infrastructure is an OT infrastructure that takes care of scenarios like power quality or network optimization. So information for those type of services is exchanged via this specific network. Also substation automation or the communication between different control centers or substations is accompanied over this IT network. So one thing I almost forgot is that another feed-in is here by electric vehicles, which are increasingly used not only to consume energy and to drive in an alternative way, but also to provide storage for energy. So they are also providing a feed-in into that ecosystem, and obviously are not only physically connected, but also via the information infrastructure. So they also provide to the overall information landscape here. So as I said, the critical or the power grid is a critical infrastructure, and this critical infrastructure needs protection. So if we look at the past and also at the last couple of years, we see that digital information processing has increased. So it started back in the 50s, and then we had home computers, we had computers that were utilized in industry and in education. We had some further enhancements in electrification and automation up to the Internet of Things or the Internet of Industrial Things. So that means digital automation and artificial intelligence has arrived in industrial automation. And this also means that the networks are more open now, and more commodity systems are also used in those industrial automation networks. And the flip side of that is that when you use standardized technology, that you're also prone to all the different types of attacks that are known for this already long existing technologies. So some of the attacks that you see down here basically utilize the fact that PCs, for instance, are being used also in the critical infrastructure. And because all of this endangers critical infrastructures like the digital grid, we need a certain security functionality to protect these critical infrastructures accordingly. So because the digital grid is a critical infrastructure, we have also regulation and legislation providing boundary conditions and providing specific requirements. You see that here there are, for instance, in Europe, we have just recently the Cybersecurity Act. We have the Network Information Directive, NIS2, and also the Cyber Resilience Act that specifically targets security for not only for critical systems, but especially for critical systems. So derived from those acts on European level are certain country-specific measures, like we have in Germany the IT Security Act or the German Energy Act as just two examples for that. We have similar approaches in France and also in UK, but not also in Europe. This is a hot topic. It's also a hot topic in US. So there are the critical infra protection guidelines from the NERC, which are enforced by the US FERC. We have different executive orders that also address cybersecurity, and specifically cybersecurity for the critical infrastructures. So this is one part of coming up with requirements in a regulatory way. On the other hand, we have the development of international standards. And this graph here tries to provide an overview what the view is of what are the essential standards that are used to protect the digital grid. So I will go through the different standards later on during the presentation. But what you can see here, those standards have a different scope. So that means they have more relevance for operation, more relevance for products, or they go more into the let's say design details or completeness. So we will come to that afterwards. But as you can see, there is a broad coverage of those standards here for the different fields. So let's start with the ISO 27000 series. So this is one series that is being used to ensure or to build up an information security management system. It's a standard, or the base standard or the base requirement standard is here framed in red. It's ISO 27001. This is the base standard providing requirements in terms of different requirements for an operator he has to fulfill. And it also provides an annex different security controls that have to be addressed. So specifically addressed, you see it on the right-hand side, are points like security policies, the organization of information security, organization of asset management, for instance, but also asset management, access control, cryptographic algorithm, not quite cryptographic algorithms, but requirements to the strengths of cryptographic algorithms, but also other things like communication security, incident management, but also more organizational topics like business continuity and compliance. And adjacent to 27001, there exists another standard, 27002. That is a code of practice, and it's essentially a catalog of security controls that are described or that are defined to address the different requirements. So those are defined in a more general way, and therefore there is an adaptation of the general requirements to specific application domains. And one of the application domain is the energy automation domain, and specifically for utilities, we have 27019, which you see here on the lower right-hand side. And that one is essentially the augmentation of 27002 to the power system automation or the energy automation domain. So this is one of the cornerstones that is applicable for operators of a critical infrastructure like the power grid, but also for vendors and contributors to that. Then we have a second standard here, which was also visible on the other slide at the beginning. This one is called 62443. It describes security for industrial automation and control systems. And this standard is a little bit different than 27001. It's a kind of holistic security standard that describes on one hand policies and procedures, like you see here. So those are all procedural security requirements. You have specific system requirements. That means there is a security level being defined on a system level, on a system level, and the security level is being defined in terms of certain security requirements that have to be fulfilled to reach a certain security level. And specifically in -3-3, these security levels are being described for systems. When we go one step further right, then we see the component and product row here. So that means here is a definition of the security product development lifecycle and also technical requirements for products. So the first one, 4-1, is important for vendors because it describes how a secure product development process shall be done. And the 4-2 describes which are security requirements for products that have to be fulfilled, also with a certain security level in mind for the technical security requirements, and with a maturity level in mind for the coping with process requirements. So what's currently ongoing is the definition of profiles. That means this one here is defined, or 62443 is defined for the industrial automation domain, and certain other domains are also adapting the standard. So it's necessary to have profiles that cope, for instance, with a terminology that is used in other domains like, for instance, railway industry or also healthcare, where a different terminology is used. And last but not least, we have evaluation criteria that allow the evaluation of coping with certain requirements that are described in other parts here in the system. So what is marked here is the maturity of the different standards and also the possibility to certify those standards. So that means that you can certify, for instance, a substation according to a system security level and in conjunction together with service providers here. That could be one certification. If you have products that are, for instance, deployed in a substation, then they can be certified according to 4-2 and 4-1. So just to give some more insights into 62443, specifically regarding the notion of security levels. So this is a picture that we saw in the slide before. In 62443, we have the notion of asset owner, system integrator, and product supplier. And the different parts in the standards are shown here, so how they interact. So that means there are certain security policies and operations and requirements for the asset owner that are posed there. And there are certain capabilities, documentation support, and also process support for the development of products that are placed on the product supplier. So, and both meet essentially here at the system integrator, which has to take care of the design and the handover to maintain and maintenance of a secure solution. So as I said, there are different security levels defined in the standard here, and those security levels range from security level 1 up to 4, and they basically are related to the assumed strengths of a potential attacker. So that means if we have, for instance, the goal authentication or user identification, then we have 4 different security levels. The first one would address user identification just as a general user. Then we have unique user identification. The next security level would be multi-factor user authentication for access via untrusted networks. And then the highest one is multi-factor user authentication for all control system access. So that means here we can see that for the different security levels, there is a requirement formulation on a technical level. Okay, so coming to the next standard, that is one of the more technical standards that can basically be used to answer or to address certain requirements, which we have seen on the slide before from 62443. So this standard is developed by IEC TC57 Working Group 15. So this working group develops a standard which is called 62351. So sorry for all this crunching of numbers and letters, but this is the way that the standardization names their documents. So 62351 is a standard that addresses the different communication protocols which are used in the power system architecture that is defined in TC57. So specifically for protocols like 6870-5-6 and also 61850 and the data models that are described in those 2 standards. So the main idea is to this is the architecture of the power systems. So you see up here the yellow ones. This is the control center, and there may be multiple control centers that are also interconnected. They are more the higher level in the architecture. Then further down, you see the substation devices and also the field devices in the substation in the blue part here. And for all of this, there are certain protocols, data exchanges defined that are between the substations, but also up to the control center and also up to further other energy management systems, like for decentralized energy resources or also for hydroelectric power plants. So common to all of those is that the data that is exchanged between the different peers needs to be secured. And secured means it needs to be ensured that the data is coming from an authenticated source, that the data has not been tampered with, and also that there may be confidentiality requirements for the transmission of this data, so that not everybody who has access to the communication line, for instance, is able to read or eavesdrop that information. So this is addressed by 62351 in also in a framework. And so let's have a closer look on 62351. So what is specifically being addressed is everything that goes into the direction of identity and access management. So that ensures an identification, authentication, and also authorization of users. And users may be human users or technical users like application or devices. And for this, the defined X509 certificates are heavily being used. A second part defined in 62351 is secure communication. And as you see in the picture here in the middle, that is actually the depiction of a substation. We have different types of communication there. That means we have communication that is being performed over Ethernet links, over IP-based links, and also over serial communication links. So that means there are different communication protocols used, so different security means need to be applied for that. What this working group does is it tries to not reinvent the wheel, but it tries to reuse existing technology, existing security technology as much as possible. So that means we are striving for more or less profiling existing standards. So TLS, which is named here, is one of the more prominent standards that we use here. And with the profiling, we achieve that the security requirements that are placed on Digital Grid are being fulfilled for the communication part. Besides securing all the communication, we also have to take care of monitoring and audit. So that means we still would like to know what is going on in the systems. So for this, we have the logging and processing of security relevant events that is also being addressed. And we, again, use existing standards like syslog or SNMP to transmit this information. Yeah, to have that all smooth going one into the other, we have the key management, and that is essential here. It's an essential part that connects all the other different parts in 62351. So that means we have certificate management addressed with specific enrollment protocols, but also the multicast communication by utilizing group-based security protocols. What's also being defined in Working Group 15 are conformity test cases. So those test cases are being used to ensure that products that implement a certain functionality by 62351 are implemented or integrated in the right way. And those conformance tests basically show that the protocol is implemented as specified. Last but not least, there are several guidelines available. Guidelines to handle the system architecture, to handle the setup of the systems, but also how to handle role-based access control in a system, for instance. Okay, so this is not to scare you, but this is essentially the interconnection of the different parts of 62351. So that relates to all the functionality that I've just shown on the slide before. So we have from an explanation, this part up here comprises the international standards and also the technical standards from 62351. And this part down here, this is the conformance testing documentation. And it mostly copes with the numbering here. So when you have a -3 down here, it correlates to a -3 up here. The only mistake that we did in the group was we didn't sort on that correlation from the first place, so it should read -5 actually here, but we started with -1. Anyway, so besides the conformance testing here, we have then the technical reports, and those technical reports are used on one hand as guideline documents, but they are also used to have a first base for discussion to to have proofs of technical concepts. So like we had in -90-1 for role-based access control, the guidelines or further guidelines, which meanwhile found their way up into the specifications up here. So the more pattern part shows you standards which just for which the work just started. So that means that this is a lively framework. So we are consistently developing that framework and evolving it. So that means there is new functionality that has to be taken account for which security is needed and is being defined. And this new functionality might also be just related to security. So I would like to emphasize here on the new part that we are just creating on migration support for stronger cryptographic algorithms. This is intended to support, for instance, addressing the advent of quantum computers and the way that we see that it is necessary to start early dealing with the migration to post-quantum cryptographic algorithms to ensure the reliability and, of the power systems, because there are typically long-lived systems, and we already see that it is necessary to start adapting those algorithms as well. Okay, so this is the substation, and in the substation I would like to map some of the standards that you have seen before. So just a short information regarding the substation. You have a field level down here. So this means you have rings of, for instance, protection devices. Protection devices can be easily described as, I would say, intelligent fuse. So there is a whole ring of protection devices which communicate with each other. So values like current, voltage, phase angle are exchanged in that ring, and depending on the evaluation of those values, a trip might be issued to avoid that there is a shortcut in the wiring, or that a shortcut has some influence on the rest of the plant. So besides that, we have the station level that is essentially doing the control for the substation, and then here we have the connectivity to, for instance, the control center, and there may also be connectivity for service technicians to do remote access, for instance. So when we look at the different parts of 62351, we have 8 and 9 for the key management and for role-based access control. Then those are mainly related to the station level here. So that means we have certificate management with the associated protocols here. We also have role-based access control, which is handled over those machines. And this type of functionality is not only available at the station level in a substation, but also in a control center. So the parts 7 and 14 are similar, applicable in the same direction here. So we have a logging server that is essentially collecting all the different log information and also forwarding that information to a more central place to deal with, for instance, security events that have been found. So for instance, if someone tries to break into a substation, then this should be this should be realized by a SIEM system, for instance, and appropriate actions have to be taken then. So maybe just as a remark, so the information that is collected here typically comes from all the different devices that are in the substation. The same is true for the certificate management that takes care of the devices which reside inside the substation. Okay, then we have the different parts that target secure communication, and that relates to the field level communication down here. So protocols like Goose or sampled values are being used here, and they are being used over multicast Ethernet. So that means that is being used to have a very to ensure very timely communication. So then we have the communication on the station level, which is 61850 MMS. And that one obviously also needs security. And we have, besides that, also the telecontrol communication. That means everything that goes outside the substation to a control center or also to a remote access technician needs some protection as well. Okay, to summarize the presentation and the information here, I would like to come up with this picture. So it shows the interconnection or the interplay of the different standards that I have shown throughout the presentation here, specifically 27000 series, 62443 and also 62351 as the three main standards that we see to secure the digital grid. I used the format here from 62443 with the notion of an asset operator, the integrator, and also the product supplier. They all have to secure their own infrastructure that can be addressed by 27000, for instance, which describes the information security management framework and can be applied to address certain regulation requirements that we see on EU level or also for North America by the US FERC. Besides that, the asset operator here has to take care of the security for the operating or for the infrastructure that he is operating. In our case, the power system automation infrastructure, like a substation that you see on the right-hand side here. So 27000 can be applied here as well. And here specifically applicable is 27019, which provides the augmentation for the power system automation domain. Besides that, we also have procedural requirements for the integrator and his own infrastructure as before, and the product supplier. For the integrator, specifically, the requirements from 62443-2-4 are applicable, and for the product supplier, we have 4-1 that, as previously discussed, describes the secure product development process that has to be obeyed when developing and producing products. Besides that, we have the notion of functional security standards, also from 62443. Here, for the integrator, the system level, 3.3, and also for the product supplier, 3.3 and 4-2, describing security controls to be implemented in products. Those blue ones here are, again, related to security levels, so they can be used to describe security controls with a different strengths of security controls. So that all only works when we have at the end the real technical measure that is described and can be applied to this to actually address the functional requirements from 62443. And here we have 62351 as a framework that basically provides technical specification in an interoperable way that allows to utilize different vendors' products also in a substation like that one up here. So I hope that this picture and that kind of conclusion here helps you understanding how the regulative side poses requirement on one hand and how the standardization side on the other hand helps to provide a secure critical infrastructure for the power grid. Before I conclude my presentation here, I would like to answer one question that hasn't been raised. One of the typical questions is, are there products available that can be utilized in substations or in power system automation? And let me jump to that slide here. So that provides some information about potential products that can be used in the digital grid to address certain security requirements like secure firmware update or secure logging that we have seen from 62443, for instance, but also in the realization by 62351. And also things like main components like the certificate management, for instance, is being supported in products already. So with that, I would close my presentation and thank you very much for listening.
Thank you very much, Stefan, for your contribution. You have highlighted the importance of digitalization. You have talked about the increasing threats from cyber attacks. Given the basic requirements along the entire value chain for manufacturers and operators, and you have expressed and you have described the existing standards that address the entire value chain and the ones dedicated to each of the actors. We will for sure remember one figure, IC 62351. This is going to be our guideline for the future. You have, at the end, talked about access, communication, monitoring, and testing for cybersecurity. Let us now go to the application. Our application will bring us to Italy, when we will talk about cybersecurity in the data exchange from distributed energy resources to the distribution system operator. Our expert here is Giovanna Dondossola, project manager in RSE, Ricerca sul Sistema Energetico in Italy. Giovanna, the floor is yours.
Hi, it's my pleasure to provide a talk on cybersecurity of data exchanges between distributed energy resources and distribution system operators, reporting a normative experience started from European regulations. Just let me introduce myself. I'm Giovanna Dondossola, leading scientist and project manager at the Transmission and Distribution Technologies Department in RSC, Italy. And I'm currently project manager of an integrated research project on cybersecurity of energy systems within a huge research program lasting 3 years from 2022 to 2024. We focus on operational technology, cybersecurity, cyber-physical system resilience, and application of artificial intelligence and machine learning for cyber anomaly detection. And my talk now it's specifically related to the DER plane controller experience. The starting point of this normative process is the European Regulation System Operation Guidelines that provides several requirements for the security of the power system operations, and in particular also establishes responsibility of data exchanges between transmission and distribution operators and significant grid users. In order to achieve a good level of power system and operational planning, security and management close to real time. This regulation has been implemented by the Italian transmission system operator within the National Grid Code and has been then approved by the Italian Energy Regulatory Authority in February 2020. Following this approval, the authority commissioning the development of a norm to the Italian Electrotechnical Committee in order to develop a project that is called Plan Central Controller within a framework that is called O16. So the norm name is CHE O16, that defines a set of monitoring control functions for DER plants in order to comply with grid observability obligations established by the European regulations, network operations needs, and also significant grid user capability to access flexibility markets. So these norms we have as now declared mandatory in a first phase for the production plant connected to the medium voltage grid with power equal to or greater than 1 megawatt. So you see here in the left side of the picture the process and I just mentioned it, and the different steps and actors involved in making these regulations active and also associated with specific technical norms. But on the right side, you see also in parallel to the sector regulation, the establishment of cybersecurity legislative acts that have, of course, impacts on the implementation of the plant central controller we are speaking about. And from the cybersecurity side, I'm just referring to the NIST directive, that stands for Network and Information Security Directive, and the Cybersecurity Act. And they are national instances that are established by Italian laws. So the combination of the sector regulation and the cybersecurity legislation in Italy has given the opportunity basically to define the cybersecurity requirements and solution for the plant center controller included in the norms I mentioned. And this cybersecurity requirement and solutions basically refer to international standard series that are represented in the slide, and I'm referring to the ISA 62443 series and the IEC 62351. So in detail, the Italian norms 016, cioè 016, includes cybersecurity requirements in two different annexes, Annex O and T. In Annex O, we have defined the procedure for performing the firmware and software upgrades in a secure way, so preserving cybersecurity during these activities. And also we have established requirements for the physical security of the hardware security module that has one component of the plant controller, and required prescribed specific compliance certifications. On the Annex T, we have defined the controller data model, communication interface, and cybersecurity profiles. Regarding the communication interface, the norms prescribe the usage for the communication between the DER and the distribution system operators. The usage of the standards IEC 61850 for sending measures and receiving set point, and in particular, of course, we have required specific semantic data models and services defined in the series of standards 61850, and their security is assured by the application of the IEC 62351 standards and related parts. We have a second interface that is somehow used for supporting services, and in particular it has to be used, shall be used for the maintaining the key and certificate life cycle active and secure. In particular, here you see the different parts of the series 62351 that are involved and related to the specification of the Italian norms. Because we are speaking about securing 61850, you see that at the communication level we have the application of Part 3 and 4 profiles, and for the supporting services we have the parts that are highlighted in the right side of the picture. And more precisely in terms of functionality that are supported by the different part of the series, we have them involved for the identification and authorization of communicating entities by using role-based access control defined in Part 8. We have communication security for 61850 exchanges, data exchanges through the application of Part 3 and 4, and the key and certificate management are supported by Part 9. Also, security monitoring is particularly relevant for the norms, and we are here mentioning security events that are defined under definition currently in part 14 of the series, and then conformance testing that is supported by specific part 103 for the part 3 profile. Back to the remote access control functionalities, we have 3 different mechanisms, so a very strong and hard cybersecurity for remote access control, and in particular I'm mentioning the identification of remote entity through the check of the certification authority certificate that are pre-configured on the controller. Then there will be the authorization that are based on role definitions. The specification of the different roles is based on what has been prescribed by Part 8, and in particular in the Italian norm, the requirements are for standard roles, but also custom roles for specific profiling, for instance, DSO operators and aggregator operators. And these roles, custom and standards, can be transported by different kinds of profiles defined by Part 8, and in particular 2 mandatory profiles are required in the Italian norms, and they are profile A and B, so roles can be transported by extended ID certificates or attribute certificates. Regarding the authentication of communicating nodes, they are performed by the protocol level, and in particular they may be performed at the transport layer level or at the application layer level. And for the transport layer, there are specific transport layer security profiles, TLS profiles, requiring mutual authentications of the communicating parties that is based on digital certificates that are signed by recognized authorities, and data integrity and confidentiality is ensured by cryptographic algorithm, and in particular there is a combination, an optimal combination of asymmetric and symmetric algorithms that are used for key exchange, data encryption, hashing, and digital signatures. So we have also performed here in the RC lab performance testing of these TLS profiles that are required by the Italian norms. Regarding the application layer, there are specific requirements for the authentication, data encryption, and integrity check of the application messages through the application of the so-called end-to-end security profile at the application level that has to be used in case of segmented communication architectures, using multiple hops between the 2 endpoints of the communications. Of course, these cryptographic algorithms make use of, we mentioned, symmetric and asymmetric algorithms that are based on the usage of private and public keys and associated digital certificates. And for managing this material in a secure way, there is the need to use and make a connection with the so-called public key infrastructure, but is based on a set of logical or physical also components, so the regulation, the registration authority, the certification authority, and the validation authorities that perform different kinds of functionalities that follows the certificate life cycle. And the most important one is the certification authorities that issue certificates or authorize other entity to do that. So both parties, so the distribution system operator and the plant owners, shall exchange their certification authority certificates. So there is the concept of PKI federations of the different parties and the PKI of the different parties. So the PKI is in charge of the life cycle of the certificates during the operational life of the communications and the communicating entities. And in particular, they are in charge of the enrollment of the controller with to its PKIs, and the renewal of the certificate when they expire, and the revocation of the certificates when the digital identity of the controller is compromised, and also the validation of the status of the certificates that is in charge of the validation authority. In order to guarantee that the prescribed cybersecurity requirements of the controller are implemented in a proper way, there are some prescriptions related to the needs of certificates and for conformity to the reference standards. And these certificates are issued by accredited certification bodies, and in particular for what concerns the transport layer security, that is based on the IC 62351 Part 3 profile, the norm prescribes compliance with the Part 103. And this part defines specific tests that are related both to expected and unusual use cases. In order to check, for instance, the key and certificate size or the time limits of the renegotiation and the resumption functions. So there are different tests that are prescribed by Part 103, and they have to be certified by accredited certification bodies. Another requirements in terms of certification is related to the second series of standard I mentioned in the beginning, that is 62443, and in particular the conformity and compliance is required towards Part 4.1 and 4.2. 4.1 is for securing the development process of the controller, and in particular a maturity level 3 is required for this part of the certifications. But for 4-2, the requirement is related to different to 7 foundational requirements that are mentioned here, but guarantees different requirements, categories of requirement actually, on identification and authentication control, use control, system integrity, data confidentiality, restricted data flow, timely response to event, and resource availability. And the security level required by the certification is shown here, and changes according to the specific context we are speaking about, so the context of DER controlling this kind of power plant having sites, as I mentioned, on 1 megawatt or higher. And finally, we have also compliance, required compliance related to the hardware security module, that is the module actually providing appropriately storing of cryptographic material, keys and digital certificate in a dedicated hardware. And for this component, the requirement is for compliance with the FIPS 140-2 level 3, so to have a resistance to physical tampering in this case. And So from the experience, I would like to provide so-called lessons learned that I think makes the experience applicable, of course, and replicable to other countries and for the same, maybe, regulation we are speaking about. So we have seen from the experience that the normative process requires a lot of interaction cycles with standardization committees and device manufacturers. So an important requirement is the technology readiness of the solutions, because, of course, this readiness accelerates the time to market of the commercial devices of this kind of controllers, supporting, of course, cybersecurity standards. So, of course, the availability of software libraries implementing the cybersecurity solutions is a key point for accelerating the time to market. And the developers of such software libraries are recommended to keep aligned with the evolution of standards, of course. So from the experience, we have seen that having controller simulator based on open libraries were quite promising in terms of interoperability check. So the preliminary testing performed with such simulators were quite positive. And having this preliminary testing also allows decoupling the development time between DSO and developments and the manufacturers that are in charge of developing, of course, the controller servers. And we also have in the normative framework the availability of a technical report including example of data models for the plant controllers, of course following the standard 61850, so they are in XML formats. And the availability of this sample data model allows to minimize possible errors in the interpretation of the norms and also facilitate the implementation work for the manufacturers. And the specification or the codification actually of the data model in XML basically refers to different parts of the 61850 standards that anticipate the new edition of Part 7.4. So we are somehow also contributing to the development of the new edition of the standards. So the preliminary functional testing of these communications between DER and distribution system operator revealed very limited interoperability issues, so confirming the advantage of adopting standard specifications and solutions. Regarding the PKI services, the public infrastructure services, we have to say that energy producer needs to interact with third-party providers of such services. And in particular, the management of the PKI is a source, of course, of complexity and also of operational costs for both parties, the DSO and the producer, so the owners of the plant controllers. Nevertheless, once these services are in place and operational, the advantages of automating the certificate life cycle management, of course, is expected to balance the provisioning costs. So, so to say, of course, is a recommended line of operation. I've also introduced the concept of federated PKI. So these concepts between different private and third-party PKIs assures reasonable security and interoperability according to certifiable standards and protocols. A possible improvements of this implementation will be the election of a single authority, having the role of trust issuers, for recognized energy sector PKIs that will provide a single trust anchor, removing the need to pre-configure on the controller the certificates related to the certification authorities that are allowed to connect to the device, so to the controller, to the DR controller. So we have also seen the case of DR plants that are not connected to internet, and in this case, according to the Italian norms, these plants shall have to manage manually most keys and certificate operations. So this is not the best, will make more difficult the implementation of the cybersecurity management process by personnel that have to be adequately skilled in order to be aware of the cybersecurity risk, so with appropriate competencies. Regarding software upgrades, I mentioned the fact that the procedure has been defined for doing these operations and actions in a secure way. So this upgrade step allowed to follow, let me say, a graded approach in the implementation of the normative obligations. So to say that we may have different steps towards the final security profiles that are required in order to meet basically what are the requests from manufacturers in terms of time of developments. And these software upgrades may also be required for strengthening the robustness of an evolving threat landscape. So we all know that vulnerabilities and attacks will increase or anyway will change in time in the future. So there is clearly the need to upgrade the software and in order to be able to tackle with future vulnerabilities and threats. And even in this case, the upgrade process will involve all actors in the value chain that are manufacturers, plant owners, and system operators. Cybersecurity upgrades may require reviewing the content of the norms. So in this terms, we need an agile process for reviewing the norms and updating devices in following, the prescriptions that will be made in place. Finally, just to conclude with a key message of my talk, I have to say that a constructive dialogue among the different stakeholders involved, mainly regulators, standard experts, operators, and manufacturers, is a win factor to achieve the shared objective of energy infrastructure cybersecurity. This dialogue plays a key role in reducing the timeline of entering into operation of secure communication and accommodating the market response speed. So that's the end of my talk, and in case of any needs, you can contact me at my email address here. Thank you.
Thank you, Giovanna, for your contribution. You have dealt with the distributed energy resources integration starting from the regulatory context. Given the technical requirements at the point of interface between the distributed energy resource and the network at the light of the standard of CHE 016, and you have spoken about the application of the standard IC 62351 to real case studies, defining profiles, defining requirements for remote access and control, management of certificate, testing, digital certificates and service providers, and caution in the field of software updates. And finally, you have informed us about the importance of the dialogue among all parties, regulators, experts, operators, and manufacturers. So thank you very, very much again. This concludes this webinar. I hope this webinar was clear and useful. Remember that the material is available from the Clean Energy Transition Partnership website. Address your questions to tri1@setpartnership.eu. We really look forward to seeing you again in future webinars. And with this, I greet you sincerely and hope for the best for your work and life. Thank you very much.